What on this computer? Okay. Oh, what's the color? Okay, that's correct. So unit 3 was about acid and bases. So it was always like the characteristic of acid is kind of different from characteristic of the base. So we started the unit off with the basic properties of acid and bases. So we should already have this on your notebook. I think it is called 3.1, property of acid and bases. So if you can look at your notebook and fill this part out, that will be great. If you don't, then we will just go over them. All right, so acid and bases, example of acids are like a lemon, lemon. And examples of bases are like soap or cleaning products. So if you, I hope you've never tasted the bases, like the soap before, but if you ever did, it tastes a little bitter. So the taste of bases will be bitter, while the taste of acid will be sour. Textures, and that's how it feels. Texture of an acid will be, I can't remember, was it? Oh, no, base is slippery. And then the acid were watery. And then the ions produced in water for acids are hydrogen ion, H+, and the bases will be OH-, hydroxide, ion. All right, so the conductivity for acid and base is the same. It depends on the strength of acid and bases. If the strength is higher or stronger, then the conductivity will be high. So both of them are conductive, yes. And the pH range for the acid will be 0 through 7, and then bases will be 7 through 14. Okay, so when the red litmus paper is dipped into the acid, then it will stay red. And if it's placed into bases, then it will turn blue. And when the blue litmus paper is dipped into acid, it will turn red. And when the blue litmus paper is dipped into the bases, it will stay blue. So the way you can kind of remember acid and base is that acids are used in red. It is depicted in red in many cases, and bases are usually depicted in blue in many cases. All right, last one, color when phenolphthalein is added. So phenolphthalein is an indicator that turns pink when it's added to the basic solution. So the bases will be pink and acid will be clear. So that's how you can fill out this chart. So because this is like a general property of acid and bases, I don't think I have to explain anything about it. But if you have any question, you can always reach out to me. And I can probably help you understand that a little bit more. Okay, so the most important thing that you should get out from this chart is that the pH range is 0 to 7 for the acid, 7 to 14 for bases. The litmus paper is one thing, but the ions that is produced in water, hydrogen plus for acid, and OH minus, which is hydroxide ion for bases, is important because that's how you can determine if something is arrhenius acid versus arrhenius bases. You're, I guess you have internet, but that's okay. All right. We're gonna move on to arrhenius acid and bases. So Arrhenius is a scientist who wanted to come up with a definition for acid and bases. And he defined an acid as a dissociating water to produce hydrogen plus, so H plus ions, which means that all Arrhenius acids begin with hydrogen. So the way you can know if something is Arrhenius acid is you look at the formula, and then if the formula starts with the H, then that one would be more likely to be Arrhenius acid, like such as example would be like HCl. Well, what else can I recall? HBr, H2SO4, those. Okay. And on Arrhenius base, dissociates in water to produce OH minus ions, which means that all Arrhenius bases contain OH in their formula. That's my last name, so you better remember. When on Arrhenius base, acid and base mix, the reaction is called a neutralization reaction. Which always produces salt and water. So typically when you see a neutralization reaction, what you will see is you will see Arrhenius acid and base making a salt and water. So whenever you're prompted to identify which one is acid, which one is base, and which one is salt and water, you have to know that salt and water is a product. It is produced. And acid and base is the one that is your reactant. So it's going to be always found on the left side of the chemical equation. All right, so the question 1 and 2 is asking you to identify which one is acid, which one is base, which one is salt and water. So like I said before, you'll be able to easily look, figure out which one is going to be the salt or the water, because we know the formula for water is H2O. So whenever we look at the product side and you have H2O and the other thing, then the H2 will be water and then the other thing would be the salt. All right, so if you look at this one right here, at the product side, we know that H2O right here is going to be water. And Fe3PO42 is going to be a salt because that is the other compound that is being made as a result of the reaction. And another way you can know if something is salt or not is if it is the product and it is ionic compound, where you have a metal and non-metal or cation and anion. All right, so if you look at the reactant side for the question 1, you see that FeOH has a, oh my God, sorry. FeOH has a part where you have OH together right here. And the H2PO4 starts with the H. So when something starts with the H, then that means that one is going to be an acid. And when your compound has OH, then that means it is a base. And that's for our Arrhenius definition. All right, same thing for question number 2. If something has OH right here, then that will be a base, Arrhenius base, because it will eventually create OH minus ion in the water. And then when you see a compound that starts with the H, then that one is going to be an acid. And then on the product side, water is easy to spot. So H2O will be water. And this SRBr2 is going to be the salt. Because as you know, Sr is a metal, Br is non-metal, which makes an ionic compound when they're together. All right. I think I can move on to the next definition for acid and bases. Any questions so far? Can I move on? Okay. Okay, the next definition for acid and bases done by Bronstein and Laurie. And the Bronstein and Laurie, these are two different persons. They wanted to come up with a broader definition for acid and base because not all bases have OH in their formula. So the definition of acid and bases needed to be adjusted. So Bronsted-Lowry acid, the acid of Bronsted, and according to Bronsted-Lowry, will donate, like give off hydrogen ion while Bronsted-Lowry base will accept the hydrogen ions. So whenever the compound is able to give the hydrogen ion, then that's an acid. And whenever it is receiving the hydrogen ion, then that is a base, according to Bronsted and Lowry definition. I will use receive. Okay, and when a Bronsted-Lowry acid and bases are combined, they will produce another acid and base combination that is called the conjugate base and conjugate acid. So the conjugate, the word means it's a partner. And the conjugate pairs are opposite of each other. So the Bronsted-Lowry acid will create conjugate base, and Bronsted-Lowry base will create conjugate acid. And they're like paired to each other, and they look very similar to each other. So therefore, the acid partnered with the conjugate base, and the base is partnered with the conjugate acid. The conjugate acid and conjugate base are always on the product side, on the right side. On the product side of the reaction. So it will be like you have acid and base making a conjugate base and conjugate acid. Okay, so the order of conjugate base and conjugate acid can be different. And the order of acid base can be different. It can be flipped around to make sure that you understand the concept. But that's a typical or general form of how Bronsted-Lowry acid-base reaction looks like. All right, now let's do some practice problems so we can show our understanding. So like I said, okay, let me try to draw a diagram so we are we know what's going on in better picture. So acid will have a hydrogen ion and it will give it to the base. And then the conjugate base will have one less hydrogen. And what's going to happen is the hydrogen ion that the base got will be given back to the conjugate base. So the conjugate acid will give the hydrogen back to the conjugate base. So, all right, let me explain a little bit better with the picture over here. Okay, so for question number 1, we see that if we compare this and that, we know that the hydrogen is, the number of hydrogen got decreased. So these two are going to be the pair, and then this one and that one is going to be the pair. And the way you know which one is going to be acid versus base is you compare the number of hydrogen. So H2O to OH. We lost a hydrogen, so which means this hydrogen from H2O is going to be given to H2PO4. All right, let's see if that is actually true. So whenever H2PO4 became a product, it gained the hydrogen. So which means H2PO4 is acting as a base, and H2O is acting as an acid in this case. So let me label them correctly with the color that I have been using. Okay, there we go. So in this case, H2PO4 is base, H2O is acid, and H3PO4 is a conjugate acid, and OH minus is a conjugate base. You okay? All right. Let's do the question number 2. We have to pay attention to what's happening a lot. Okay, so that was question 1. Question 2, H2O and H3O will be a pair again. I'm just gonna draw it. And H2PO4 minus and HPO4 2 minus will be a pair again. And I hope you can notice that H2O became H3O means it received a hydrogen from the other compound. So H2O will be acting as a base. And let's see if that's true. H2PO4 right here lost the hydrogen when it was going to the product, when it became a product. So that means the hydrogen from H2PO4 is given to the water, which is H2O, and then this H2O became H3O. Therefore, this is how you would identify them. So H2PO4 for question number 2 is actually acting as a acid. And H2O in this question 2 is actually acting as a base. And that resulted in HPO4 2 minus to be the conjugate base. And then H3O plus will be conjugate acid. Right, that's how you would identify each one of them. If you want to see a particle diagram that depicts this process, then you should visit the lesson that covers Bronsted-Lowry acid and base, which is on unit 3. And then that will be probably lesson 2 of that unit. All right. Now we're going to move on to 3.4, which is strong versus weak solutions with percent dissociation. So percent dissociation is a term that we use to describe what is a percentage of dissociated ions when the acid is put into water or base is put it into water. And this is really, really, really easy to remember, because if something is not 100%, then they are weak acid. So if something is 100% dissociated, then it's strong solution. Okay, so let's go ahead and fill in the blank. So percent dissociation measures the percentage of total dissociated ions in the solution that have dissociated or broken apart into the ion. The more molecules that is dissociated, the stronger. Okay, so what we mean by that is these are not dissociated. These are dissociated. So as you can see, these two circles are attached together, but these two circles are separate. So it's measuring how many of them is being separated. All right. So hang on. Okay, I'm gonna write a note right here. If 100% dissociated, then it is strong. Less than 100 is weak. Okay, so we have two pictures right here. And then if you look at it, the first picture, picture A, if you observe how many molecules that is present in this one, you have four. You're looking at four different molecules, but if you look at it closely, they're not dissociated at all, which means this one, the picture A, would be weak solution, while picture A is like all the way separated, all the way dissociated. So that means the picture B would be strong. Okay, we're moving on to the very last section, which is when we talk about the pH of strong versus weak solution. Okay, so pH stands for potential. What is really? Okay, P stands for potential. I'm not sure what strength. It measures amount of hydrogen ions. Let me search that one because I'm not sure. Oh. Potential of hydrogen. Okay, so acid have pH lower than 7, which means there are large number of hydrogen molecules. Bases have pH more than 7, which means there are higher number, lower number, smaller or small number of hydrogen molecules. Okay, so let me explain this part. So I was just going through the sentence. Okay. Okay, so we went over the pH range for acid and base. If something is less than 7, then those are acid. If something is more than 7, those are bases. If since it's a log scale, you have to picture the concentration of hydrogen like in reverse way, because the lower the number, you have more concentration. Higher the number, you have higher the concentration. That's the typical way you think of it. But for pH scale, if you have like 0 or 1, then that means it has a lot of hydrogen in the solution. If the pH is close to 14, then that means you have very, very small number of hydrogen that is present in the solution. So that is what it's saying. So I'm going to read from here. Acids have a pH lower than 7, which means that there are a large number of hydrogen molecules. Bases have a pH more than 7, which means there are a small number of hydrogen molecules. pH is not always an accurate measure of solution strength, so acid or base, but it will always tell you if a solution is acidic or basic. So if you can only see pH, however, the closer a number is to 7, because 7 is a neutral, the weaker the solution it is. So if you are given both pH and percent dissociation, you should always use the percent dissociation to determine its strength. So percent dissociation to determine its strength. All right, so question number 1 right here is going to be a question where you are only given pH and you're supposed to figure out if it's going to be weak solution or strong solution. Okay, if that's the case, so solution with the pH 2 is far away from 7. So that one is going to be strong. And since it's less than 7, that is going to be an acid. So pH 2 would be strong acid, while pH 5 is close to 7, which means it's going to be weak. And because it's less than 7, that's going to be a weak acid. All right. If you look at B, solution with a pH 8, pH 8 is really close to 7, but it's higher than 7. So it's a base, but it is also weak base. So it'll be weak. Weak base. And D, solution with pH 13. 13 is a little far away from 7, so that means it's going to be stronger. So strong base will have about pH of 13. So strong base. All right, so like I said before, pH should be used to determine if it's going to be acid or base. And the percent dissociation should be always considered to determine if it's going to be strong or weak. And we're going to do combination of this right here below. Okay. Do you guys have these answers? Okay. I'm going to make this larger so I can write it better. All right, so we have solution A, B, C, D. The first thing we're going to do is determine if it's going to be acid or base. So solution A, it is at pH 6.5, which is less than 7. That one is going to be acid because it's less than 7. Solution B, pH 13, higher than 7. So that one is going to be base. Solution C, this one has pH of 2, so that's less than 7. So that's again, it will be acid. Solution D, which has pH of 8, which is higher than 7. So the solution D is going to be a base. All right, now we need to look at the percent dissociation on each diagram to decide if it's going to be a strong or weak. All right, solution A. Do you see any molecule that is being dissociated versus not? So this one, you don't see any molecules that is dissociated. So 0%, oh no, Okay, 0% dissociation, which is weak. So this one is going to be weak acid. Solution B, you see all of them are being separated. So that one is like near 100% dissociation. So solution B would be strong. Base. Solution C, you see some of them are not dissociated. So this one is still considered as a weak acid. Although the pH is 2. All right, solution D, you see every single one of them are dissociated. So it's close to 100% dissociation, which means that one is going to be strong base. Just because the percent dissociation in this picture is 100%. So if you see 100% dissociation, then that's going to be the strong solution. If you see some of the molecules that is not being dissociated, then regardless of the pH, that one is going to be weak solution. All right, so that sums up the unit 3. If you have any question, don't hesitate to reach out to me via email. But that's everything that I have for this period. Let me see. Let me stop the recording.